Hey guys, in this video I'm going to go over what you are going to be doing for your molecular geometry and bonding part 1 lab. It will also pertain, a lot of the information will pertain to molecular geometry and bonding part 2. So with this, hopefully you notice that when you go into the questions, the regular problem area where you answer your questions, you see one question. There is where you're going to upload your document that contains all of the information for this lab. So to get that, you need to go under your questions printout. And once you're in your questions printout, you're going to click on the molecular geometry and bonding questions. So go to read, and then you're going to open this with some sort of PDF viewer. If you have some sort of mobile device that you can draw on a PDF, or you're going to want to actually print this out and then upload that document onto CSE Pub. So I just put it into iBooks myself, and from here you can just answer it and then save it as PDF and then input it again onto CSE Pub. So you're going to go through, you're going to answer your pre-lab, and then you're going to go and answer your actual lab, which has your Lewis dot structure, your VSEPR sketches, and your geometries. So you're going to go through, do it for all, 10 structures? 14 structures. So you've got 14 structures that you're going to be giving information for. And we're going to go over a couple of them today. So today I'm just going to go over my usual pre-lab lecture. And hopefully that will be enough information, especially if you guys have not gotten to this information in class. Hopefully it'll be enough, but if not, please send me an email or come to my office hours on Monday, Wednesday, and Friday from 10 to 11:30 on Microsoft Teams. If you're having trouble accessing those, let me know. Okay, so a Lewis structure, hopefully you guys already know, is a structure where we've got electrons being shown as dots and then bonds being shown as lines. A Lewis structure is there or is made in order to show us what type of bonding we expect a molecule to exhibit. And with this bonding in the structure, we can find out a lot about the chemical reactivity of species. So Lewis structures are very important to understand in order to understand what's going on with a molecule. Lewis structure itself is going to be based on the number of valence electrons. So when you, it's supposed to be when you are doing a Lewis structure, you need to know your number of valence electrons. So this is just kind of a review of how to determine your number of valence electrons for anything within the periodic table. We are talking about molecules with Lewis structures, so we're talking about this region of the periodic table. We don't care about any of the rest of it. So over here, we have group, it's actually 13, 14, 15, 16, 17, and 18. If we are in group 13, we have 3 valence electrons. 14 is 4 valence electrons. 15 is 5 valence electrons. 16 is 6 valence electrons, so on and so forth. So just using our periodic table, we can say, okay, this atom has this many valence electrons. Once we have our number of valence electrons, we can use that to figure out our electron configuration, like we've done here. And we can also use it to find our Lewis dot structures. Lewis dot structures are going to be showing the actual bonds. So here we have NH3. NH3 has 1 pair of electrons all by itself, unshared, and then it has 3 pairs of electrons that are shared, so they're generally written as lines to indicate that they are a bond. I'm going to go with a different color. Let's try green. So these are our bonds that we see right here. So lone pairs are going to belong just to the atom that they are attached to. So these right here. And then our bonding electrons, those are going to be shared electrons that are shared between the 2 atoms of the bond. In order to make a Lewis structure, the first thing that we're going to do is assign the available electrons. So we're going to count up valence electrons. see that right there? Let's try this. So you're going to assign electrons. So for each atom, determine the number of valence electrons. So this will be what we see on our periodic table. Once we have assigned numbers of valence electrons, we are going to sum them to get the total number of valence electrons. Okay. Then keep in mind that if we have a charged species, we're going to have a different number of electrons than our pool would give us initially. If we have a positively charged molecular ion, we're going to subtract the number of electrons equal to the charge. If we have a negatively charged ion, we're going to add electrons equal to the charge. So we're going to add them all together, and then we're going to assign a central atom. So when we look, our central atom is going to be generally the one that's written first. And it's going to be the least electronegative, with the exception of hydrogen. Hydrogen is never a central atom. Okay, so after we have chosen that central atom from number 3, which a lot of them are going to be carbon, we're going to arrange the atoms around the central atom, and we're going to add bonds between the central atom and the peripheral atoms. Every electron or every bond that we add is 2 electrons, so we're going to subtract those electrons from our electron pool. Next, we are going to insert electrons around our peripheral atoms. So we're going to place electrons in pairs around our peripheral atoms until we have an octet. And then once we have an octet on our outer atoms, we're going to move inwards to our central atoms. So any remaining electrons that are left, put them on the central atom. We will then check and make sure all the atoms within the structure have an octet. These are going to be our exceptions. Hydrogen will never have an octet, it will only have 2, and boron and aluminum generally only have 4 electrons around them. If we have octets for everything, besides hydrogen, boron, aluminum, we are good. If we don't, if we are lacking octets, we're going to move electron pairs from non-bonding positions into bonding positions. Okay, so we're going to move from adjacent atom to the octet deficient atom. Okay, now if we do that, what we're going to form are double and triple bonds, where a double bond is when we have 2 pairs of shared electrons between 2 atoms. A triple bond is 3 pairs of shared electrons between 2 atoms. After we've done that, our next step is to assign formal charges. We assign our formal charges with the following equation. Formal charge is equal to the number of valence electrons of the neutral atom, so given from our group number. We subtract our number of covalent bonds, and then we subtract our number of unshared electrons. Keep in mind that your bonds, if you have a single, that counts as 1. A double is 2. A triple is 3. And when we're talking about unshared electrons, it's talking about each individual. 1. Okay? And then whatever this formal charge is for the atoms, when you sum up all of the formal charges from all of the atoms, that will equal the charge of the molecular ion. So your sum of your formal charges, if you have a molecule, will equal 0. Your sum of your formal charges, if you have a molecular ion, will equal the charge of that molecular ion. And what we get is a Lewis structure that looks something like this. We have a central atom. In this case, we have 2 central atoms. And then we have peripheral or terminal atoms. We have single bonds, double bonds, or we can have lone pairs. Now, hopefully you guys are familiar with Lewis structures already, which is why I went a little bit fast. But next I want to talk about the idea of VSEPR. valence shell electron pair repulsion theory. Right there, just VSEPR. So this talks about what type of geometry a molecule will achieve in order to minimize repulsion between the electrons in the valence shell of that atom. So when we're talking about VSEPR, we are talking about the molecular shape around a central atom. So if we think about a Lewis dot structure as a 2D structure, our VSEPR structure will be a 3-dimensional structure, so taking it off the page. Okay, so some terms that you guys need to know are electron groups. We also call these electron domains. And these are grouped around the atom which contains electrons in pairs. So that could be any type of bond or a lone pair of electrons. Either one would be considered a electron group or electron domain. So if we have a single bond, we have one electron domain. If we have a double bond, we have one electron domain. If we have a triple bond, we have one electron domain. If we have a lone pair of electrons, we have one electron domain. The bond angle is the angle that's formed from 3 atoms together. So if we only have 2 atoms, so if we only have an A and a B, we don't really look at VSEPR for that because that is not a structure with a bond angle. Okay. Next, electron group or electron pair geometry or electron domain geometry. This is going to be the geometry of the electron groups. So if we think about our groups of electrons or domains of electrons, those are going to be used to determine our electron group or electron domain geometry. And then we have molecular geometry that is a derived electron group geometry. So it's going to have the same geometry, same geometry around our central atom. We're just going to ignore the lone pairs when describing the structure. So what do I mean by this? So here I've got, sorry about that. Here I've got all of the VSEPR geometries that we're going to be seeing in this lab. So it is based on the number of electron domains or groups. So we can have 2, 3, 4, 5, or 6 electron domains around a central point or a central atom. If we have 2 electron domains around a central point, we have a linear structure. So it has a linear electron pair or electron domain geometry, and we also have a linear molecular geometry. If we have 3 electron groups around a central atom, we're going to have a trigonal planar electron pair geometry, and it looks like a little triangle all in one plane, which is why it's called trigonal planar. With our trigonal planar geometry, we have 120 degree bond angles. And I didn't say this just a minute ago, but hopefully you realize that with our linear, we have 180 degree bond angles, which is why it's called linear. With our trigonal planar, with our 120 degree bond angles, we have our 3 groups as far away from each other as possible. Now, we don't really see this with our linear, because if we remove one of the electron groups, we no longer have a real VSEPR type of structure. But with trigonal planar, if we take one of these atoms, and replace it with an electron pair, we are going to change the way that the atoms look. So in our initial structure, our atoms looked like a triangle in a plane. If we look at our structure made, if we look just at our atoms, when we replace one of those with an electron pair, we get a bent geometry. So if we have a trigonal planar electron geometry and one of the electron domains is a lone pair, we call that a bent molecular geometry. Okay, next, 4 groups around a central point. If we have 4 groups around a central point, the farthest we can get those groups away from each other is 109.5 degrees. It looks like a tetrahedron. It's kind of hard to see because I'm not a very great artist, but it's a little tetrahedron, so it has 4 sides. There we go. Let's try that. So it's got doop, 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 doop. There we go. That kind of looks like a tetrahedron. So the peripheral atoms make a 4-sided structure, which is why it's called a tetrahedron or tetrahedral. If we were to take one of the atoms of our tetrahedral structure and change it into an electron pair, we no longer have this atom right here. So what happens is we have our central atom, and then our 3 bottom atoms like this. And here we now have what we call trigonal pyramidal. We have a triangle base right here, and it forms a pyramid shape. So that's why it's called trigonal pyramidal, where our central atom is up right here, and all of our atoms make what looks like a triangle-based pyramid. And then if we take another one of those atoms and replace it with another pair of electrons, we go back to having a bent structure of our atoms. Our next type of geometry that we see, and I'm just going to keep this nice and clean over here, is a trigonal bipyramidal. So with a trigonal bipyramidal, we have 2 triangle-based pyramids, which is what's got that bi. So we've got a triangle base like this. And then on that triangle base, we've got a pyramid shape like so. So 2 pyramids that are fused together. Here is that base right there. Those 3 atoms make up that base. And then we've got our top part of our pyramid. So trigonal, excuse me, trigonal bipyramidal. Hopefully you see from this picture, although who knows. It's got 2 different bond angles. So we have 90-degree bond angles, and we have 120-degree bond angles. So we have 3 what are called equatorial positions, so the atoms that are at the equator, and those are going to be 120 degrees from each other. So the ones at that triangle base, they're all 120 degrees from each other. And then we have what are called axial positions, these 2 right here. So our axial positions are 90 degrees from those equatorial positions right here, and then they're going to be 180 degrees from each other. Combined, we get our trigonal bipyramidal structure. And again, we have different structures based on how many electron pairs that we have around our central atom, replacing those atoms. So we replace atoms with electron pairs. When we look at our trigonal bipyramidal geometry, our electron domain geometry, we can see that we have all 5 electron domains occupied by atoms in this structure. And when that is true, when all of our atoms or all of our electron domains in our trigonal bipyramidal structure are occupied by atoms, our structure will have the same molecular geometry as our electron domain geometry. So in the case of all atoms, our trigonal trigonal bipyramidal geometry will be trigonal bipyramidal molecular geometry as well. If we take one of these groups and we replace it with an electron pair, we get what's called the sawhorse geometry. Now, first I want to point out where that electron pair has gone. It has gone into one of the equatorial positions, and that is where all of those electron pairs are going to go. The whole idea behind VSEPR is that we're trying to get our electron pairs to minimize repulsion. So we're getting them as far away from each other as possible. And because our axial positions are 90 degrees from three, axial positions are 90 degrees away from three equatorial positions. So our three equatorial positions, here, here, and here. Our axial position is going to be 90 degrees from those right there. If we put electron pairs on our axial positions, then we're going to have a lot more repulsion than if we put them onto our equatorial positions, where our equatorial positions are only going to be 90 degrees away from two positions. So our equatorial positions are going to have a lower amount of repulsion versus our axial positions. So electron pairs themselves are going to have a smaller effective nuclear charge, and as such, they're going to spread out more, and they're going to be more repulsive than our bonds themselves. So anytime we put lone pairs around a central atom, in most cases it doesn't matter, but in the case of trigonal bipyramidal, it matters. We're going to always put those onto our equatorial positions. Okay, so our first one we get a seesaw or sawhorse position, molecular geometry rather. And so the reason that we call it that is because we put it kind of on its side. It looks like this. It's going to be a wedge right here, dash right here, and it kind of looks like a seesaw. So you can imagine these two positions right here going back and forth like a little seesaw, or if you look at it the other way, it can look a little bit like a sawhorse. Okay, our next one, we remove another atom and replace it with a lone pair. We get what's called a T-shape, and the easiest way to see this T-shape is to kind of move this structure a little bit, and it'll actually look like this. So our two axial positions and then the one remaining equatorial position. And then one more equatorial position being replaced with a lone pair gives us a linear geometry because the atoms themselves are in a linear arrangement. So if we have three pairs of electrons in a trigonal bipyramidal structure, then we are going to have a linear molecular geometry. Next is our octahedral, and last is our octahedral, where we have 6 electron domains. These electron domains are going to be 90 degrees away from each other. So it's, again, hard to see this, but we have a kind of square base, and then it all comes up to this point right here. And maybe you can see it, maybe you can't, but we have 4 sides right here. We're going to have the same thing on the bottom, where we have 4 sides, so it looks like a little octahedron. Okay, so it's called octahedral because it makes an octahedron shape with the atoms. Like so. Okay, with our octahedral electron pair geometry or electron domain geometry, going to our molecular geometry, if we have all of our positions occupied by atoms, our electron domain geometry and our molecular geometry are going to be the same thing. If we take one of those electron pairs and one of those atoms, and we replace it with an electron pair, we get a square pyramidal shape. So we have this structure right here. We have these atoms making up our square base, and then this atom at the top making it look like a pyramid structure with a square base. And of course, we have our central atom. So it forms a square pyramidal if we have one lone pair in our octahedral for our molecular geometry. If we take and we replace another one of those atoms with a lone pair, this is another one where it's specific to which atom is going to be replaced. We are going to take the one that is furthest away from the current lone pair so that we can get those two lone pairs 180 degrees away from each other. And what we get is what's called square planar. So we're removing this atom right here, basically, and we get, erase this one right here. We get a square in one plane, so square planar. If we go ahead and replace another atom with an electron pair, we get a T-shaped, so like this again. And then one more, we get a linear arrangement of our atoms. And that is everything for our geometries. I do want to, real quick, do a couple of examples. So I'm going to go onto a different sheet here for that. As soon as I figure out where it's at, there we go. So let's do an example or two of these. I think there's probably more examples on CSE Pub in the pre-lecture video from, or pre-lab video from Dr. Meyer. But just in case, I want to go ahead and go over a couple of the examples, just so I make sure that you guys get all the information from here that I can give you. Okay, so we go on to our packet. Let's go ahead and just go into our packet right here. Let's try arsenic pentafluoride. Sure, that looks great. Oh, let's go into iBooks so I can write. Arsenic pentafluoride. Okay, so first thing we want to do is we want to draw our Lewis structure. So, and when we draw the Lewis structure, we should get a structure that looks like this. This is an expanded octet. Voila. So this is arsenic pentafluoride. We can see arsenic pentafluoride is going to have 5 electron domains. And all the electron domains are atoms. So there are 0 lone pairs. Okay? So our VSEPR sketch, this is where we want to bring geometry into this. So here we have our central atom, which is arsenic. I always like to draw my equatorial positions first. So there is one equatorial position, one is going to be coming towards us, and one's going to be going away from us. So this wedge that we see here means that it's coming towards us out of the plane of the paper. The dash means it's going into the plane of paper away from us. And then our 2 axial positions here and here. So that is our VSEPR sketch. You do not need to add the lone pairs in your VSEPR sketch for anything but your central atom. After we do that, we're going to do our electron domain geometry. Our electron domain geometry is based on how many electron domains we have. We have 5 electron domains, so this is trigonal bipyramidal. And our molecular geometry is going to be the same as our electron domain geometry because we have 0 lone pairs, so this is also going to be trigonal bipyramidal. Okay. Ooh. Let's try another example. I did not mean to do that. Boop, boop. There we go. Let's try hydronium. There we go. Let's try hydronium. So when we do hydronium, ooh, there we go. I can really see. Hydronium has a Lewis structure that looks like this. Okay. And then when we draw our VSEPR sketch, again, we want to make sure that we have our geometry about here. So this is a tetrahedral. So it has 4 electron groups, or electron domains. So this is going to be a tetrahedral electron domain geometry. And then it has 1 lone pair. Okay, so when we draw this on our option here, we need to have our lone pair. You can either draw it as dots or you can also draw it as arrows if you prefer. Either one will work, like that. And then with the tetrahedral structure, you're going to have a dash and a wedge and a line, like so. So any tetrahedral structure, some X, you have 2 things in the plane, one in front and one behind when we're showing our VSEPR sketch. Okay, now we have a tetrahedral electron domain geometry. And since one of these electron domains are a lone pair, we envision what the molecule looks like if we don't think about the lone pair itself, and we see that we get trigonal pyramidal. So we have a triangle base and a pyramid structure. Okay, let's try sulfur tetrafluoride. So sulfur tetrafluoride, oops. There we go. If we draw the Lewis structure for this, it looks like the following. Like so. So here we have 5 electron domains. So our electron domain geometry is going to be trigonal bipyramidal. And one of those is a lone pair. So we have a seesaw or sawhorse shape. I personally like seesaw because it looks like a seesaw to me. But if you look here, it kind of looks like a sawhorse. Okay, so we want to go ahead and draw out our structure. Same idea that we did above, right? So we have our shape of our trigonal bipyramidal. We'll have our axial and equatorial positions, like so. So we're just going to replace one of those y's in the equatorial positions with a lone pair. So we have our sulfur, we have our lone pair right there. We have our 2 fluorines in their axial position, and then our 2 fluorines in our equatorial positions. Okay. Let's try 2 more examples. Let's try sulfur hexafluoride. Sulfur hexafluoride has a Lewis structure that looks like this. And then this structure has 6 electron domains, so we know that our electron domain geometry in this case is octahedral. There are 0 lone pairs, so our molecular geometry is also octahedral. So when we're drawing an octahedral geometry, we're going to have our central atom. We're going to put an atom above and a below, like so. Then we're going to have 2 on wedges, 2 on dashes. So that's one way of drawing octahedral. That's the way that I generally draw it, but you will also see it like this. But just keep in mind that no matter what, these are 90-degree angles. Okay. Again, I like to draw the first one, so that's the one I'm going to draw. So I'm going to have my sulfur in the center, fluorine above and below, fluorines on our wedges, and then on dashes. Okay. And let's try one more. Let's do xenon tetrafluoride. So here, if we were to draw, our Lewis structure, we'd have xenon here, surrounded by our 4 fluorines. Xenon, by the way, is one of the few noble gases that will actually bond. It's because it has the orbitals are so far away from the nucleus that they're a little bit more reactive. Okay, so here we see that we have 6 electron domains, so our electron domain geometry is octahedral. And we have 2 lone pairs, so we get square, planar for our molecular geometry. So when we're drawing our VSEPR script, make sure that we put our electron pairs 180 degrees away from each other, and then the rest of it will be drawn like we've done for the other one. Okay. If you guys have any questions about how to do any of this, please send me an email or come to my office hours Monday, Wednesday, Friday from 10 to 11:30. I will see you guys later.